Well, I think we can start, Misha.
Okay. Yes, thank you. Okay, so I'd like to thank organizers for the opportunity to make this talk. Okay, so I'm going to talk about global conformal blocks on the torus in different contexts. One of these contexts is within the Казимира approach. So I'm going to provide you with all definitions. So here, it's important that global means SL2. Okay, so let me go to, okay, so yeah, first of all, this work is, this report is based on the following works. And in collaboration with Konstantin Alkalaev and Semyon Mandrigin, and the last work by myself. And motivation is following. So actually, we are interested in calculations of one of the Virasoro 1-point block. Because this block is important in different applications, so it was first studied in the context of AGT correspondence, and and there are some connections with blocks with 4-point blocks on the sphere. And yeah, the thing is that closed expression for the 1-point block on the torus is still unknown. There are some approaches, but the closed expression is still unknown. So, but it's difficult to calculate. So in order to do that, we go to consider blocks which are governed by subalgebra of the Virasoro algebra, which is SL2. It's like, yeah, it's like, it could be understood as large C limit of the Virasoro blocks under some, or we start from the Virasoro algebra and then make some contraction, and at the C tends to infinity. So basically it's, this restriction, so yeah, these SL2 conformal blocks are some some piece of Virasoro block, but they are more simple, so we are interested in them. And there are two other points to highlight, but I'm not going to describe them during this talk. This is just some interesting points. So the first one is it is 3CFT correspondence for the blocks on the torus, and it requires calculation. It requires some calculation of Wilson lines on the side of the ADS3, and so in this context, our results could be quite useful because because this is results from the CFT side, and you could compare them with ADS3 results. And the last one is the application to integrable models. We know that on the sphere, 4-point blocks could be considered as like a wave function of some models, which are Colliger models. Then here there is no such a clear I know correspondence between wave function of some model, we don't know, and conformal blocks, but it could be, maybe it could be interesting to to go this way. Okay, so here is a plan, and basically there are 3 points that I would like to highlight. The first one is okay. So first of all, of course, I would like I'm going to give you some definitions. Then we will focus on certain type of blocks on the torus. We call them necklace blocks, and we describe the importance of these blocks. So basically, we will show how these necklace blocks produce blocks of the arbitrary topology. And this is like the first thing to highlight during this talk. The next, we are going to proceed to Казимира equations for these necklace blocks. This is so I'm going to review the sphere case, and then I'm going to show how to derive these equations on the torus. And finally, having these equations for the necklace blocks, we will discuss their solutions and how to construct these solutions, and how to construct these solutions independently. And in the light of this, the Казимира equations, which were derived previously, could be quite useful in order to check our solutions. So this is it allows us to not only have some functions for conformal blocks, but we can check them. So okay, this is the plan. Okay, so let me start from definitions. So we consider conformal field theory on the torus. So tau is fundamental period, and as usually we introduce the modular parameter. And as I mentioned, we consider SL2 blocks. So we have, instead of usual case of Virasoro symmetry, we have SL2 symmetry, and which is local symmetries. Basically, we have two copies of the SL2 R algebra here, and global symmetries are U1 plus U1. So it's like usual symmetries on the torus. So then we see, okay, so there are, of course, well-known commutation relations for SL2 algebra. And we focus on the highest weight states, which are defined as follows. Okay, and since we are going to consider primary operators, I will remind you that in conformal field theory, there is a operator state correspondence. So in the third equation, we could introduce primary operators through the highest weight states as follows. And so this is their definition. And actually, we are going to consider correlation functions and then conformal blocks of these primary operators. And okay, and as usually on these operators, we could realize we could use the differential realization of SL2 algebra, which is the following. This is actually it's quite standard, but it's going to be useful concerning notations in the future. Okay. Having these primary operators, we could go to correlation functions. So here, since we know the partition function on the torus, we could construct correlation functions in the second equation here, where this trace on the Hilbert space of the theory could be written as follows. So could be written as follows, which is basically okay. So this trace could be written as follows. So we consider the trace on all states in our theory. So D here stands for the spectrum of conformal theory. So we consider like a trace on all states in our theory, primary states. And then in each state, we sum over descendant states, which is given by this second sum. And we can see that there are, so this is like a full formula for the holomorphic and anti-holomorphic sector. So this is basically the definition of the correlation function on the torus. Okay, but we are more interested in not in correlation function, but in conformal blocks. So, so we have to expand this correlation function into conformal blocks. And in contrast to this sphere, there are basically two main ways to to do it. So, okay, so let me return to this formula. So this is, so here we have a string of n operators. And what can we do? We can consider operator product expansion between two operators, which gives us an infinite sum, but with some operator, but this operator acts on the one operator instead of two. So so basically, so doing OP, we reduce n-point correlation function to n-1 point correlation function. Okay, and there is another way that we can insert these projectors between any two operators. And as I mentioned, in contrast to the sphere case, these two approaches gives us different conformal blocks. And so as usually we so we have like two principal options. And the thing is that yeah, as I mentioned, these are two different approaches. And the thing is that if we consider like the pure OPE channel, which means that we only take in OP between primary operators, the conformal blocks are known. So like they were found by Krauss and Coulters in this article. But there are an opposite case when you're only insert projectors, and these blocks, so we call them necklaced blocks. They are unknown in a closed form. I mean, there are some expansions, but they are not known in a closed form. So, okay. Are there any questions on this sort of decomposition?
Yeah, I have a question.
Okay.
In the paper Krauss 17,
Mm-hmm.
You mean the endpoint torus?
Yeah. In this paper, they found endpoint torus conformal block, but they use only operator product expansions. So okay, so they found that this torus block can be written as one-point torus block. Okay, so they found that endpoint torus block can be written as a product of one-point torus block and n plus 2 block on the sphere. So they basically, for the OP case, they found like closed expressions.
Yeah, I see.
Okay. Yeah, and on the other hand, there is no expressions for necklace blocks, and then it's okay. Then it could be quite useful to derive, like to study this case. Okay. And the thing is,
me, I'm sorry, I would like to ask you, what do you mean under the conformal fields here in your approach? I mean, in the usual sense, the conformal field should be killed by some number of operators of Virasoro algebra, which have positive modes.
yes,
But
yes,
you can see, but as far as I could understand, you consider order only SL2 subalgebra. So
yes,
it means that you have infinite number of conformal fields with respect to this subalgebra, but a finite number with respect to the total Virasoro algebra. Is it right?
Okay, so okay, let me think. Okay, so we so you refer to like
Yes, I mean just
to
these
this condition
equations.
basically.
So sometimes these fields are called quasi-primary fields. They killed only by the primary with respect to global conformal algebra. And
With respect to SL2.
only with to SL2. And of course,
Okay.
yes.
I see. So the number of conformal fields is infinite.
Yes,
Yeah,
yes.
Actually,
yes.
any Verma model of Virasoro algebra is infinite sum of Verma models for SL2.
Okay, thank you.
Okay, thanks.
Sorry, but I continue with my previous question of the endpoint torus block regarding this paper. When you have endpoint torus block, you have multiple different conformal blocks
Yes,
with different channels.
yes.
This specific relation you mentioned about the torus block with the sphere is for which channel?
Okay. Okay. Yes. How to? Okay. So, yeah. Concerning the channel, actually, for any, like, okay. Actually, they derived it for any channel. Let me slightly describe it. So, as I mentioned, the the connection between torus blocks is the following. So n-point torus block can be written as a product of 1-point torus block and n plus 2 sphere block. And on the both sides of this equation, you have some channel, and basically these channels should coincide. I mean, like how to express it in different ways. So
Yeah, I understand what you mean.
Okay. So actually, yeah, like to explore your question, actually, they didn't, I know they didn't give us some exact functions, because it requires like the knowledge of n plus 2 point block on the right-hand side of this equation. And these blocks are not, I guess there are some ways to construct them, but they are not really known for like any channel. So
Okay.
okay. Okay, so okay, so yes, so we okay, so since we okay, so we defined the necklace channel block as a conformal block when you put this projector between two of the fields. Okay, and then let me, I know, okay, it's quite useful to consider some lower point examples in order to, I know, reveal the difference between these two channel blocks. So there is a picture here. So on the first picture, we have a 1-point block. And for 1-point block, there is no channels actually. And this is just a diagram of this sort. But if we have two fields, like we can insert projector between them, or we can do OP. So these pictures B and C correspond to this case. And actually, so the idea here is that conformal block C, which correspond to the situation when you take OP between two fields. So this block can be expressed through the this block because effectively when you take OP, you have one field instead of two, and then you return to 1-point block again, and so with action of some operator which is in operator product expansion. So yeah, like effectively, if you know this 1-point block, you could produce 2-point block, and actually it applies to any blocks. I mean, yeah, and the conjecture is following. So you could obtain any block of any channel topology through the necklace blocks. For example, if we look at the picture 2 and consider like this first field is not a real, it's not a primary operator in the correlation function, but something which goes from OP. Let me kind of, okay, I could draw something here. Okay, could you see my screen now?
Yes.
Okay, and let me. Okay, so we can consider like this 3-point block. Yeah, so here we have field number 1. Field
No,
number
actually,
2.
we don't see what you're drawing. We only see your slides.
Ah, okay. Sorry. Okay, now it's better.
Yes.
Okay. So we have this block when we have two fields. Okay, like so we have like O1, O2, or 3, and we take operator product expansion between these two guys in order to obtain some like I know. So here is going to be some OP operator which acts on the family OP. Yeah, and then here we have the third field. And the idea is simple, that after taking this OP, we could rewrite this operator product as this. So it's going to be this thing, which is actually which stands for this part of the diagram, and this is actually the necklace block. So I know, in other words, like having any channel, we can drag these OP operators on the left and calculate block, and only then act by this product of the operators in order to find our block. So it means that actually we can consider only these necklace blocks, which consists, so these blocks are actually blocks of this type. So this is just a circle and some operators. And we can produce any topologies from these blocks. For example, I could act by by OP operator on this necklace block and obtain the block of the following topology. And in the light of this, these necklace blocks are, I know, some basic conformal blocks in the space of all conformal blocks. And if we know necklace blocks, we can compute any block of any channel topology. So yeah, okay. So let me return to my slides. Okay, in the light of this, it's like it's necessary to know some expressions for these blocks. And okay, so first of all, we want to analyze these blocks in the framework of Казимира approach. Let me slightly remind you about the Казимира approach on the sphere. So it was considered in works by Olin and Dosborn. Okay, so we can start from the 4-point block on the sphere, and so here an expression, and we can consider the this irreducibility condition. So basically, we are doing the following. So we have a Казимира operator in our algebra, which is known operator. So we can put this Казимира operator to this bracket in order to have the eigenvalue of this Казимира operator. Okay. So here the left hand side stands for these like a conformal block with the Казимира operator inserted. So Казимира operator is right here, and if we can commute we can commute this Казимира operator with our primary operators in order to obtain some non-trivial equation. And basically, so instead of course, we can calculate this 4-point block directly. We know, so we know these matrix elements, and we can calculate it directly. But this approach allows us to derive an equation on the conformal block. So yeah, and this is quite well known. So it's more, it's more useful to derive equation for the function g here. So this is like a standard function of the cross ratio, and the result is given here. So we so within this Казимира approach, which is basically to insert Казимира operator here and then commute in order to obtain this differential operator. So doing that we can obtain the differential equation for function g. And this is almost the hypergeometric equation, and solution is given here, which is very well known global block on the sphere, which is given by hypergeometric function. And this is quite useful approach. So we and basically the first part of our work is to do the same thing on the torus. So we have a Казимира operator here, and actually so here let us start from the 1-point torus block. It was done by Krauss in 2017. So, and the idea is like the following. So we could consider, so we have a Casimir operator, and we could insert this Casimir operator into conformal block in order, so we have like this equation. So, which is quite obvious because this trace is basically, let me explain it a bit better. So this trace is actually these brackets. So if we insert Casimir operator next to this bracket and act on this, we just obtain some we obtain the eigenvalue of this operator. And the only thing that we should do in order to derive the equation is to realize this Casimir operator as a differential operator in terms of modular parameter. And it's quite understandable how to do it. For example, if we consider this operator, which is Q multiplied by derivative of Q, it gives us L0 because it acts here and L0 goes before this. And in the similar fashion, we can realize this part of the Casimir operator by some differential operator. And of course, actually, the 1-point torus block is a function of modular parameter and coordinate of the primary operator, but we remember that there is a Yard identity which is associated with the global symmetry on the torus, so we can actually exclude the Z dependence. So we have a only Q dependence, and I know doing that we derive this equation. So okay, so it was derived in the Krauss paper, which is once again almost hypergeometric equation, and the solution of this equation is given here. So yeah, this is okay. Once again, despite the fact that 1-point block is so 1-point block on the torus was very well known, so it was derived by in like I guess in 2009. This is another approach to this derivation, which is quite useful, and because it requires some simple operations like I know commuting this Casimir operator with these two operators and looking at what we have. So here we have this, and then we apply this technique to necklace blocks. So in the necklace, so here in 1-point torus block, there is only one opportunity to insert this Casimir operator. So we can insert it only here because it acts on the brackets in this trace. In many point necklace blocks, we have several brackets because we insert projectors, and these brackets are in projectors. So in, I know, for example, 2-point block, in 2-point necklace block, we have two opportunities to insert this Casimir operator. And actually, we can consider these as the two equations of this form. And okay, so doing that, we could derive the system of Casimir equations for n-point blocks in the necklace channel. So this system is like a given here. Okay, so this is n. So here it's n partial differential equations for in terms of modular parameter and in terms of insertion points. So these separators L are these separators which acts on the points of the insertion of primary operators. Okay, so this system of n equations for the function of n insertion points, which here they are denoted by z and modular parameter q. So we have function of n plus 1 variables, and then it should be supplemented by Yard identity. So we have n plus 1 system of the n plus 1 equations for function of the n plus 1 variables. And that is quite complicated system. We don't really know how to find a general solution of this system. Or
question. You mean that for each primary field in the population function, you could insert you may insert this Casimir operator, and each insertion give one
yes. So actually so for example here first equation is when,
for example, FNN means that this is the block when you insert in this block in the what is the meaning of FN?
Okay, FN is a n point necklace block. So here J stands for like position of this Casimir. So you could insert so you could insert Casimir before everything. This is the first equation, yeah. And if you have two fields, in order to obtain block, you are inserted project. So you inserted projector between them, and if you want to obtain the second equation, you have to insert Casimir next to this projector. So it gives you the second equation. So, and since you were inserted n minus 1 projectors for n operators, because you have to insert them between. So this, you have n plus 1 additional brackets when you could put Casimir operator. And this is the origin of these n minus 1 equations. Okay. So in the case of Krauss work, the equation were different, and in his work there was a factorization of so this block was factorized in the product of 1-point block, which depends on the Q only, and some sphere block, which depends on these Z points. Here we can see that there is no such a factorization, and these are much more difficult system. And but it's like but its system could be quite useful if we want to check some functions that we can compute in other way. And this is like our next topic. So
Excuse me. I'm sorry. If you can take another finite dimensional SL2 subalgebra in the Virasoro algebra and find out to write out some Casimir operator for this subalgebra and obtain some another equations, does it make sense? I mean, there is a lot of SL2 subalgebras in the Virasoro algebra. So you can take Ln and L minus n, and a commutator of these two operators gives you L0. So you obtain a triple of operators of SL2 algebra.
Okay.
Not quite, because there is a shift, right? Integer shift, central charge.
Okay, you can redenote the Cartan operator as L0 plus this shift.
Okay, I guess it could be interesting to test. I honestly, I don't really know. Okay, it could be interesting to test. Yes. But I know your assumption is okay, so your idea is like more about going to Virasoro algebra. But here we can like consider only SL2 subalgebra without any associations with Virasoro. So I guess it could be useful, but not directly in this context.
But if I understand, your SL2 subalgebra comes from Virasoro algebra.
Yeah. But this is like the greater idea to like I know to move from the SL2 algebra to Virasoro algebra. Now we are focused only on the SL2 algebra, but it could be useful in order, I guess like I guess more generally, is your question about application of this technique to Virasoro blocks, for example?
Yes, but I would like just to understand the idea, because there is a lot of SL2 subalgebras in Virasoro algebra, but you, by some of the reasons, took some special one which starts from L minus 1, L0, and L plus 1.
No, the reason is that other subalgebras, so L minus 1 acts is a very simple way, just a derivative, but L minus 2 is something complicated. That's why, yeah, the blocks will, it acts on correlation function in complicated ways, right?
Yeah, so you
will obtain something much more complicated.
Okay, yeah, simplicity is the argument.
But in this way, you could, I don't know, I'm not sure, but I just think you can obtain in this way infinite number of equations. Maybe they are self-consistent and could and allow to find a solution for conformal block in some another way.
Okay, I guess. Okay, it's interesting. Maybe I guess I could elaborate it, but okay. I don't really know the answer right away. Okay, so from this moment we can think about these equations as a test field, and having this equation, we could return to back to torus correlation functions. So here like we remember this expression for torus correlation functions, which which includes this matrix element in the second line. Okay, so and our idea to calculate this element is following. So we have these states here, and okay, so let us use operator state correspondence in order to go from this matrix element to the correlation function. And yeah, so some details about it are following. So we have this arbitrary descendant state SL2S descendant state, and the operator realization of this state is following. So these are just derivatives, and derivatives are differential realization of the operator L-1. And so here the next line is just complex conjugated version of this. And in the light of this, we can we can express this matrix element through n plus this is n point. So this is matrix element with n operators, and we could express it through the n+2 correlation function, but with these derivatives and these limits. And and here is the crucial moment that this is like n+1, n+2 correlation function. And okay, and the idea is to forget that these operators actually are on the torus. Because we prefer to consider them as operators which lives on the sphere in the following sense. So we know like torus can be obtained by so torus can be obtained by compactification of the complex plane, and here which we want to do, we want this correlation function, n+2 correlation function, to live on the sphere. It means that we we just go to spherical coordinates, and we don't really think about, I know, some boundary conditions, and because on the torus there are boundary conditions, and we just wanted to see what happens. And okay, so what we got that torus correlation function could be expressed through this n+2 correlation function. And if we move to conformal blocks, we have to insert projectors between any pair of operators. And then we can think about this identity not on the language of correlation function, but on the language of conformal blocks. And after that, we can find the relation between torus blocks and some other blocks which lives on the sphere. So, and I know a great thing about it is that these blocks that come from this correlation function with a certain channel decomposition, they are known. Like so they are known, and then we can just use expressions that were obtained before. So in light of this formula. So yeah, basically I'm saying that okay, so basically I'm saying that torus conformal block in the necklace channel can be expressed through conformal block on the sphere, but with two additional operators and infinite number of derivatives and some limits, like here. And okay, so this is quite complicated, and in order to analyze cases when this block in the left-hand side of this formula can be found, we should analyze these conformal blocks. They are called comp channel blocks, and they were obtained by Vladimir Rosenhaus in like 2019. And this is an expression for n-point global blocks. So, okay, let me explain it. So this is an expression. It consists of two pieces. The first one is some prefactor, which is function of coordinates, and the second piece is comp function, which is given here. This is some sort of hypergeometric function. And for example, this is a hypergeometric function of k variables. And if k is 1, this is just a usual hypergeometric function f to 1. And the parameters of this is called comp function. So the parameters of these comp function, so they are expressed through dimensions of block. And okay, so this is the function, and what we want from this function. Returning, okay, actually we have to take this function and first of all make this inversion, and then take derivatives, but derivatives with respect of z0 at zn+1. So from this really hard function, we just need to extract dependence on z0 and zn+1. Yeah, and of course, in the general case, it's quite difficult, like having this function and then take an infinite number of derivatives and then sum it up. But the structure of this comp block, I know it. So there are some simple cases when this differentiation and taking sum over m would be simple. Okay, in order to do it, we can okay, what we want to consider. For example, consider a1 and a2 to be 0. So if they are 0, we have Pochhammer symbol of 0, which is 0 if this number is not 0, and 1 if we have like a Pochhammer symbol of 0, 0. And so actually, if we put a1 to be 0, we have this index to be 0 to be 0. And actually, it I know. So then there is no summation of n on n1, and the same applies to nk. And this is useful because the dependence on z0 and zn1+1, this dependence is this dependence is only in these two guys, in the first one and in the last one. And if we reduce this sum from the infinite sum on n1 and nk to only one term, which is 1, this is going to be much more simple. And this is our approach. So we put these parameters in the comp function to be 0. And so for the simplicity, for the I know our future needs, we introduce them with the opposite sign. And So yeah, the thing is that if we consider these guys to be 0, the comp channel block is just some polynomial function in terms of z0 and zn plus 1. So here is an expression for any s1 and s2, but this is just leading term. So we will discuss only case when s1 equals s2 equals to 0. And having this function, which is polynomial, we can easily do our operations. So we have to do this inversion, then take an infinite number of derivative and then sum it up. And yeah, it could be done because it's just a polynomial function. And in this case, we also use a new notation with the S1 and S2 in the superscript. So it's for the case S1 and S2 to be 0, we obtain this form of necklace block, which is okay. So we have some function of Q, the first insertion point and the last insertion point, and here we have endpoint block. So there is a sort of factorization here as it was in the Krauss work. But yeah, so here this block G with tilde is like conformal block with the following set of external and this set of intermediate dimensions. And this is like I know explicit result. Unfortunately, we don't really we didn't really find some generalization of this result to integer s, because for integer s we don't have we don't have such a simple form of the comp function which led us to simplifications in calculations, but we had like quite simple form, but we didn't compute the general block for integer s. Like our main result is for s1 and s2 to be 0. But we did it for lowercase blocks. For example, for 2-point block, we found such a identity, which is like which is the following. So for integer s, we have like a block which is which corresponds to case s equals to 0, multiplied by this function and some polynomial of q and x. So x here is just for 2-point block is just a ratio of insertion points. And we described some features of these polynomials, but it's not, fortunately, it wasn't really successful. So these formula are our main result. And okay, so having this formula, we could, having this like expression for endpoint necklace block, we could return back to Казимира equations. And actually, we can just check it. So let me remind you that we have these.
Yeah, just can you explain me what is in terms of the decomposition? What is com blocks?
Com block is when your
this graph exactly.
Okay, let me. Okay, let me just demonstrate you. So sorry, 1 second. Okay, so com block is when you're okay. So when you are on the sphere and you have like okay, so first operator, second and then you have then you use OP between them, and then third, and like this is block of this topology. Like here it's sorry, it's not 3, it's like a 4, 5, and here are intermediate dimensions which comes from OP. So this is the block of that topology. So here like or n minus 1. Okay. Okay, so, and yeah, the funny thing is that if we okay, yeah, I like completely forgot to mention that there is a interesting geometric interpretation. So if we like consider this comp channel block on the sphere and consider these two guys to be connected, actually we have some circle with like the first here and the operator number n here, and this is basically, from the topological standpoint, this is our necklace block. So this choice of channel is not like random. Okay. Okay, so having this expression, we return to Casimir equations. And okay, so just to remember, just to remind you that there are n of them, and we can just substitute. Okay, if we substitute this guy into these equations, we are going to obtain some equations for this function jn. And the thing is, if these obtained equations are Casimir equations on the sphere, which are very well known, then we we can say that we checked our result. And basically this is the case. So in this system that I showed you from n equation, the first one were trivial. And we have like these equations, and after substituting our block into this equation, we can see that this system of equation reduces to correct system of equation on the sphere block. So for example, the first and the last equation reduce, so they reduce to Casimir equations for the external fields. And after that, we have like n minus 1, which is trivial, and minus 2. So we have n minus 3 equations for intermediate channels, and they have exactly a right form. So like this is so then after substitution we obtain the correct system of Casimir equation for this block j with tilde, which means that we check our result using Casimir equations. And yeah, basically this is I know the essence of our work. So I guess that's like it. Let me just slightly remind you 3 main results that we discussed. So first one is that necklace blocks are generating blocks. So in the light of fact that any blocks of any channel topology could be obtained from the necklace blocks. And then I describe the ways of deriving the system of Casimir equations for the necklace blocks, and we obtain from basically direct calculations, we obtain this block under this condition, and we checked this block using Casimir equations that we derived previously. So like I know it's quite useful because it gives us yeah, despite the fact that we didn't find some closed expressions from necklace blocks for any parameters. Like I just to remind you that this result was derived under this condition. It's quite useful concerning, for example, analytic properties of these functions, and because it's really difficult to find them explicitly from expansions. And also we get this nice factorization, so which allows us to to check this result, and this is quite interesting. So yeah, I guess that's it. Thank you for your attention.
Thank you. Questions, please. Yeah, we had quite enough questions during the talk, so but
Misha,
somebody
maybe I
else,
have a
yes.
question more.
Okay, yes,
Go ahead.
Juan, please.
First, you try to solve this, for example, for some value of n, and this system differential equation.
So this system.
For example, for n, for some value of n, what was the main problem that you faced?
Okay. Actually, okay. So this system equation, we tried to solve this system for n equals 2, and actually the problem is not to solve this system. So we actually know the we know how to express the necklace block in terms of in terms of some series, yeah, and you could put this this series into these equations and solve it. So this is a solution. Our idea was to maybe these equations could help us to find some some solutions in terms of hypergeometric functions or any sort of special functions. So so there is no way to solve these equations in terms of series with certain properties, but it's not like closed expression. Or is this the answer or not? Or maybe your question was different.
Yeah, I mean, more or less was my question, like, because I mean, the difficult you found by solving this, or by
okay. Okay, so yeah, so here there is no there is no division between insertion points and modular parameters. So this is quite difficult. I don't really know how to and so yeah, you see, for example, in the second line, there is this mix of Z and Q, because Z are in these operators L, and it's quite difficult to it's quite difficult to distinguish them. Or you could think about some new variables which are combinations of Q and Z, and this is not really. So yeah, I don't really know how to solve this system for general parameters.
One more last question. Have you thought try to find some holographic description of your result?
No. Unfortunately, yeah, despite the simplicity of, for example, this result, I haven't tried yet. So I guess there are there is okay. So first of all, there was a paper on this type of blocks, but they consider only degenerate representation of SL2. So basically H is minus J divided by 2 when J is integer and it's not 0. So for this block, for these blocks, they derived some holographic description, but for this case, I don't know, and I haven't tried. So,
I mean, for a general value of n.
No. I don't really know.
I mean, the paper you mentioned is for which n?
Oh, okay. Let me think. I guess it was paper which is written by Belavin and Alkalaev.
I see. Okay.
I guess they considered, for sure they considered 2-point block.
2-point, right.
I guess maybe there are some like generalization, and actually, so it's quite it's quite interesting question. So for these parameters S, which I put to be 0, you see that, so S are given in the like a pre-last line. You see if H are negative integer, and for example H1 equals to H alpha. So okay, okay. So sorry, let me think a bit. I mean that S1 equals 0 can be obtained by can be obtained by some certain some certain values of H1, H alpha, and H0 with tilde, but they could be integers, like so I mean actually this is like in this paper they considered all dimensions to be integer, but like my idea that we can obtain some results by setting some of the dimensions to be integer, negative integers, sorry. Like so yeah, basically there are some works on the holographic description, but I know haven't tried to apply it to these results. Maybe I should. Okay, thanks. May I ask a question? There is okay, so there is a hypergeometric equation for 4-point block on the sphere, yeah, and actually quite the same equation for 1-point block on the sphere. So my question is this like so how to say it? Are there any connections? So you know that there are some connections between 4-point blocks on the sphere and 1-point block on the torus in general. As I remember correctly, it's like in the Virasoro case. So it was like derived in your work with Fatiev, Navier, and that's it. So, and my question is the connection between this hypergeometric equation, is this like some is this the same, or is it something different in your opinion?
Well, yeah, I believe that, well, it can be different because, well, just the same function. And I believe this relation is obtained from that relation in the large central charge.
Okay, because
seems like
because people
conjecture.
Because people mentioned something like this, and I know this comment was the only comment that I can say, but okay, I guess I guess like this is this form of this relation. Okay, thanks.
Okay. there are other questions, please go ahead. If no, then let's thank Misha for nice talk.